Swayam Prabha. Digital India. Educated India.
Good morning. Now we will start discussion on the module characterization of wastes. In the introductory module, we have discussed that all type of wastes are not suitable for energy production, and we have also come to know that those wastes which are suitable for energy production can also produce energy through different routes, not with the same route. That is why, to understand whether a particular waste will be suitable for energy production through a particular route, we need to understand the properties of that waste. So, characteristics of the waste is very important, and this module will be used to describe the processes which are used to characterize the waste and how the properties are determined. So, basically we have solid waste and liquid, that is waste water. So, we will be dividing the whole characterization module into parts. The first two parts will describe the characterization of solid waste, and the third part will describe the characterization of liquid, that is waste water. So, in this part we will be discussing most of the important properties of solid waste except that energy content or heating value. So, we will be discussing the physical and chemical properties and mentioned here proximate and ultimate analysis, fusing point of ash, then lignocellulosic composition and leaching properties of the solid waste. So, what are the physical properties of solid waste? Some important physical properties are mentioned here, that is specific weight or density, then particle size and size distribution, permeability or hydraulic conductivity and moisture content. So, at first we will discuss on specific gravity or density. We know that specific gravity or density is defined as the weight of any material per unit volume. So, that is kg per meter cube, that is a unit in a system, and the density may be of basically three types: absolute density, apparent density and bulk density. Say if we have one material, say we have some wood, piece of wood. So, if we get the sawdust from this, the wood dust from it, so the particle size will be smaller, or we can keep more number of chips and store in a truck. So, in these three situation, if we use the smaller particles, or we can use some chips here and we can use it, store it in a very big volume like this. So, if we consider one volume V here, same in this, if we consider volume V, and here also if we take any volume V, say here we are taking V. So, these three V are same, volume is same. So, mass M1, M2 and M3, this M1, M2 and M3 will not be same. So, here the M1 will be more, then this and then this. That means, the less M or less mass in this unit volume or volume V is because of the incorporation of interparticle void space and the void space inside the particles. So, here also the interparticle portion is less, the contribution of interparticle void space is less, and here both are less, the particles are considered only. So, this is absolute or skeletal or true density, and this is apparent density, and this is our bulk density. So, these are three types of density are used to characterize the solid waste, and on application point of view, the solid waste are basically having relatively bigger size. So, bulk density and apparent density will be much important, but when we will be using some catalyst for the processing of the solid waste, at that time this true density of the catalyst will also be important. So, how can we measure the density? The density can be measured by pycnometer. So, there are two types of arrangement, that is true density and tap density analyzer, and the principle is the Archimedes principle of replacement of volume of the gas. So, as discussed just now, that this is the M3 by V, this value can be increased by compression. So, some example is given here. So, if we take loose municipal solid waste, no processing or compaction, if the density is say 90 to 150 kg per meter cube, but this can be increased to 355 to 530 kg per meter cube by compaction in the truck. Next property is particle size and its distribution. Particle size is very important, because different type of reactors we will see in later modules, that the reactors have some capacity to handle certain range of particles. So, particle size is important to understand whether this will be suitable for using in a particular process or not, and the determination of that particle size can be done by basically three approaches as shown here. The one is the trommel. When the particle size is relatively bigger, the trommels are used, and this is very suitable for municipal solid waste having bigger particle size. Intermediate particle size materials can be, the particle size can be determined using sieve analysis, and when the particles are very fine particles, then we can go for, that is, particle size analyzer using some camera. So, now we will discuss particle size distribution. So, we have come to know that these are three different approaches through which we can determine the particle size, but in a mixture of solid waste, all the particles will not be having the same dimension or same size, there will be some range. All the particles may have different size, but very similar or within certain range. So, the distribution is also very important. So, one example is given here. Now, what do we mean by distribution? Say if we use one sheep shaker, so say dV average, d average, say d average 1, d average 2, d average 3, d average 4, d average 5. So, we have different screens, pan, and there is some other top also. So, this is the screens just as shown here, different screens are there. So, after certain time we will get the material into different screens. So, here we will getting some M1, say or M0, M1, M2, M3, here we will get M4, here you will get say M5, like this. So, correspondingly we will get the total, and this is for M pan. So, we will get the total if we ignore this one and this one. So, that will be our total M1, M2, M3, M4, M5, our corresponding X1, X2, X3, X4, X5, that is mass fraction. So, X1 is equal to M1 divided by sum of M. So, this is the mass fraction. So, that way it is reported here that mass fraction is this one. So, d average 1, d average 2, d average 5, we are getting different mass fraction. Now, with this mass fraction we can plot like this. So, X1 just we can plot. So, d average 3, 4, 5. So, d this one, say this one, like this is x. So, d average, d value this direction and y axis x. So, that is differential plot, the same information we can present in that way, or the same information we can present in this way also. The one is cumulative oversize and cumulative undersize. So, this is called cumulative presentation of the data and this one is called differential presentation of the data. So, both way we can present the data for further understanding or better understanding of the distribution of the particles into different fractions. So, here oversize cumulative, oversize means when we will consider one screen, the material which will be on it, retain on it, oversize, which will be passing through it, undersize. So, that way we will be getting this type of nature for oversize and this is for undersize cumulative. Now, hydraulic conductivity is another property of the solid waste because it helps the percolation of water through it. So, this is tested because to know in landfill leachates how the water is going through the layers under the earth. So, to understand this, the hydraulic conductivity is measured and the factors which affects this hydraulic conductivity is particle size, fabric, degree of saturation, pore geometry, properties of the test fluid, but it is not so easy to measure this one for the municipal solid waste because they are heterogeneity in nature. Then moisture content can be measured by heating certain amount of solid waste at certain temperature and that temperature is equal to 105 degree centigrade until constant weight. So, all the water will be vaporized and then we will get the remaining material. So, loss in weight is proportional to the weight or the moisture content of it. So, that is percentage moisture is equal to loss in weight divided by weight of material taken into 100. Now, we are coming to chemical properties of the MSW, municipal solid waste or any other solid waste. So, here proximate analysis, ultimate analysis. At first we will discuss the proximate analysis. So, in case of proximate analysis we can determine fixed carbon, we can ash content, we can determine moisture content and volatiles. So, when we will take some solid waste and we heat it at very high temperature in absence of oxygen, then the volatiles will go off, but we will not allow for a longer period of heating, for a small period of heating at high temperature. So, volatiles will go up and the mass loss will be proportional to your volatiles and then we will use the material and heat it under certain condition for longer period in presence of oxygen. So, that all the material is burnt and the metals which are present in it that will be converted to ash and the direct amount of material present that will be proportional to the ash content and then moisture content already we have discussed. So, the remaining will be the fixed carbon. So, fixed carbon equal to 100 minus moisture minus volatiles content minus ash content. So, at first the moisture content is determined, same sample is used for volatiles determination and then for ash determination and by difference fixed carbon. So, ultimate analysis, that is CHNS analyzer, the basic principle of the CHNS analyzer is that all the elements carbon, hydrogen, nitrogen, sulfur will be converted to oxides. So, C will be converted to CO2, H will be converted to H2O, so S will be converted to SO2, N will be converted to NO2, but this NO2 conversion is not so easy as the temperature maintained here is around 990 or 1000 degree centigrade. So, part of the nitrogen is converted to NO2. So, the first job for the determination of CHNS is the combustion. So, sample will be combusted at higher temperature and then the flue gas will be produced in oxide form CO2, H2O, NO2, SO2 etc. Then that will be carried by some carrier gas and will pass through some reduction zone. So, some reduction means some tubes are there filled with copper granules. So, copper granules will use the oxygen and reduce the NOx which are generated. So, nitrogen will be produced. After that will be some mixture is required for the proper mixing of different gas components here. Then separation of the gas components, this separation is basically done using some chromatographic column, so gas chromatographic column. So, depending upon the nature of this gas molecules, the retention time will be different. Say if we have one column, in this column say gas is going having all the components CO2, H2O, N2 and SO2, and this column is filled with some adsorbents. So, that materials will be having different capacity and different attachment capacity. So, the less reactive materials will come first, then the lesser one, then the lesser one. So, retention period will be different, and when the gas is coming out, we will be using some detector. So, that detector will detect what is the component is coming and what is the concentration. So, this is the mechanism for the determination of ultimate analysis or the CHNS content in it. So, as shown here SO2, H2O, CO2, N2, this type of spectra we can get in GC depending upon the different retention period. Some examples of CHNS analysis of different materials are shown in this table. Now, fusing point of ash. So, fusing point of ash, that is the temperature at which the ash content of the solid will be fused. So, if we think about the mechanism of this, so basically we will get number of steps. The first is shrinking of the solid waste, that is shrinkage temperature, then further heating, deformation temperature. If we give more heat, then hemisphere temperature, that means the solid ash, the ash is gradually going to be molten, and this is intermediate stage when hemispherical form appears, and then if we increase the temperature further, it will be flowing, that is flow temperature. So, these are the temperature which have been reported, and step by step this situation comes. And for the determination, this can be determined experimentally by using some furnace, and people have tried to develop some mathematical relationship, that is empirical models through which this can also be determined. And for that the composition of the ash is required. What are the metal oxides present in it, like say SiO2, CaO, K2O, MgO and Al2O3, what are the composition on it? If we can understand, then some empirical formulas are available. So, that can be used to calculate the ash fusing temperature. Next we will discuss on the determination of lignocellulosic components. So, that is lignocellulosic biomass are having lignin, cellulose and hemicellulose. So, we have to determine the concentration of this, and this also the lignocellulosic biomass also contains some amount of volatiles. So, our objective here to determine the extractives, cellulose, hemicellulose and lignin. So, how can we determine the extractives? As the term indicates, that is it is extracted from the solid by using some solvent. So, that solvent is basically benzene and ethanol in 2:1 ratio. So, we add some certain amount of solid waste in this solvent and keep certain time and provide certain conditions, then the volatiles will come out to the solvent. Then the condition is here at fixed temperature for 3 hours agitation, and then after leaching the residue is dried in hot air oven at 105 degree centigrade, so that all moisture is going out. Then the dried sample is cooled in desiccator and weighted. So, if that mass is M1, MO minus M1 by MO, MO minus M1 by MO, that is initial mass how much we have taken, now how much we have present. So, that is the loss MO minus M by MO into 100, that is the extractive percentage. Next is hemicellulose. So, hemicellulose can be dissolved in alkali solution. So, this property is exploited to determine the hemicellulose content and certain strength of NaOH solution, not very high strength, it is 150 ml NaOH solution 20 gram per liter, N by 2 solution is taken. Then in this case 3.5 hour recycled is done with distilled water, and after that the residue is washed with distilled water till no sodium ion is present in the wash water. That means it is the material is made free from the sodium hydroxide. So, the dried sample is cooled in a desiccator and weighted, and the amount, if it is say M2, then Wt is equal to M1 minus M2 divided by MO. That means after the separation of the extractives the sample is taken. So, M1 minus M2 divided by MO, this is the percentage of the hemicellulose in the solid sample. Next is lignin determination. So, lignin is not soluble in acid and alkali, it is very less solubility it is having. So, but cellulose can be dissolved. So, sulfuric acid is added here, the concentrated sulfuric acid, that is 72% concentrated acid is added at 8 to 15 degree centigrade for 24 hour, and the mixture is diluted with 300 ml of distilled water and boiled for 1 hour with recycled distilled water. So, this is the procedure for the digestion of the materials in the H2SO4 media. So, that cellulose will come out and then lignin will be in the solid phase. So, after separating it, after the cleaning, then it is washed with the water, and then the residue is dried to a constant weight and cooled in a desiccator and weight. So, this weight is say M4. So, the lignin content is equal to M4 into 1 minus W1 divided by M3 into 100. So, what is this W1? Small w1 is equal to capital W1 by 100, thus capital W1 is extractive percentage. So, extractive percentage by 100. So, 1 minus this into M4 divided by M3 into 100 is the lignin content as reported by this fuel processing technology. This journal in 2004 it is reported. Now, determination of cellulose. So, cellulose is determined by that 100 minus W1 minus W2 minus W3. So, this is the determination of different lignocellulosic components in solid waste. Now, we will discuss how to determine the leaching property of the solid waste. So, leaching property is necessary because this is not desirable. Is from solids, if some toxic chemicals come out, that is not desirable. So, some conditions are produced which are very similar to the conditions which prevail in landfills. So, different types of toxic chemicals have been investigated, their leaching capacity from the waste, like say 8 heavy metals, 12 organic solvents and 17 pesticides have been tested. So, for the testing of this leaching property of the solid waste, basically extraction method was used. So, extraction vessel, and then extraction vessel are of basically two types. One is zero head space extractions, in this case there is no head space, another is with head space, we are having some head space. So, the previous one is important for the case when some volatiles material are present in the solids, like say acetone, benzene, N-butyl alcohol, carbon disulfide, carbon tetrachloride, chlorobenzene, chloroform, etc. When these are present in the solids or in the waste, so this setup is used. In other case, this setup is used, that is bottle extraction vessel. Now, we need some extractive or extraction media. So, what are those requirement? Reagents and extraction fluids. We need the extraction fluids, that is fluid 1 and fluid 2. We see here the pH is higher in the case of 1, that is acetic acid and sodium hydroxide, both are added in this case, and here extraction 2 when pH is very less, 2.88. So, only acetic acid is added, no sodium hydroxide is required. So, two types of extractive fluids are used depending upon the nature of the pollutants present in the waste or solid waste stream. So, up to this in this part, and we will discuss the heating value of solid waste in the second part of this module. Thank you very much.